Imagine standing on a remote mountaintop in Chile, the night sky sprawling above you like an infinite canvas dotted with ancient lights. It's July 1st, 2025, and the Atlas Telescope, part of NASA's Vigilant Network scanning for cosmic threats, picks up a faint blip. At first, it seems like just another speck in the vastness, but as astronomers crunch the numbers, hearts race. This isn't a routine asteroid or a familiar comet from our solar system's fringes. No, this is something far more extraordinary, an interstellar visitor hurtling toward our sun at a blistering 137,000 miles per hour, defying the gravitational norms that bind objects to our stellar neighborhood, dubbed 3I/ATLAS, or formerly C/2025N1 ATLAS. It's the third confirmed interstellar object ever detected, following in the enigmatic footsteps of 1I/Oumuamua in 2017 and 2I/Borisov in 2019. But this one, it's rewriting the rules, sparking debates that blend hard science with the thrill of the unknown. As we stand here on September 29th, 2025, with fresh data pouring in from telescopes worldwide, let's dive into this cosmic saga, a tale of discovery, mystery, and the relentless pursuit of truth that could reshape our understanding of the universe. Picture the scene. The ATLAS telescope in Rio Hurtado, Chile, captures the initial images, revealing an object streaking in from the direction of Sagittarius, near the heart of our Milky Way. Moving at 61 kilometers per second relative to the sun, its hyperbolic trajectory screams outsider. Unlike objects born in our solar system, which orbit in elliptical paths, 3I/ATLAS is on a one-way ticket through our backyard, unbound by the sun's gravity. Confirmed as interstellar by the Minor Planet Center on July 2nd, it immediately draws the gaze of the world's premier observatories. The Hubble Space Telescope snaps its first portraits on July 21st, showing a puffy coma, a hazy envelope of gas and dust surrounding the nucleus about 277 million miles from Earth at the time. This isn't the cigar-shaped glow hinted at in early rumors. Instead, it's a dynamic, evolving cloud that hints at volatile ices sublimating under the sun's distant warmth. What makes 3I/ATLAS so captivating isn't just its origin, potentially from the thin or thick disk of our galaxy, making it possibly older than our 4.6 billion year old solar system, but its bizarre behavior. It began showing activity far beyond Jupiter's orbit, where sunlight is too feeble to melt water ice in typical comets. Yet here it was, already outgassing, forming that telltale coma. The James Webb Space Telescope turned its infrared eyes on it August 6, 2025, revealing a chemical cocktail dominated by carbon dioxide alongside water and carbon monoxide. Early analyses suggest a CO2 to water ratio that's exceptionally high. Estimates point to around 8:1, the highest recorded for any comet, far exceeding the norms in our local comets. This chemistry screams alien in the truest sense. Not extraterrestrial life, but forged in a stellar nursery with conditions wildly different from ours, perhaps a colder protoplanetary disk where CO2 ice dominated over water. As the object races inward, NASA's fleet mobilizes. Hubble, JWST, SPHEREX, and even Mars orbiters like ESA's Mars Express and ExoMars Trace Gas Orbiter pivot to study it, with perihelion, the closest point to the sun, slated for around October 30th, 2025 at about 1.4 astronomical units, AU, or roughly 130 million miles. Scientists have a narrow window, about 5 months from discovery to its vanishing act into the interstellar void. But the clock is ticking and the data is flooding in. Ground-based telescopes like the Very Large Telescope, VLT in Chile, detect cyanide, CN, on August 14th and atomic nickel vapor on July 20th. Common in comets, but intriguing in this context. Swift Observatory spots tentative water vapor and hydroxyl, OH, radicals between July 31st and August 1st. These aren't just random detections, they're the universe's fingerprints, revealing what this wanderer is made of and where it might have come from. Transitioning from the raw thrill of discovery, let's peel back the layers of what separates 3I/ATLAS from its predecessors. Oumuamua was rocky, oddly shaped like a cigar, and showed mysterious non-gravitational acceleration without a visible coma. Borisov was more comet-like, with a tail and familiar chemistry, but 3I/ATLAS. It's a hybrid enigma. Its coma appeared early, driven by CO2 sublimation. CO2 turns to gas at much lower temperatures than water, explaining the activity at distances where our comets stay frozen. Yet recent observations show no detectable non-gravitational acceleration, which is puzzling. In typical comets, outgassing jets act like tiny rockets, nudging the trajectory beyond what gravity alone predicts. The absence here implies an anomalously massive nucleus. Estimates suggest a mass over 33 billion tons, with a diameter larger than 5 kilometers, possibly up to 20 kilometers. That's orders of magnitude heavier than Oumuamua or Borisov, raising eyebrows. Why so massive? Is it a dense rocky core wrapped in ices or something else? This mass anomaly fuels speculation, but science demands tests. JWST hunts for spectral lines, CO2 at 4.26 micrometers, water at 3.05 micrometers, CO at 4.67 micrometers. Visible light scan seeks cyanogen at 388 nanometers, the C2 swan bands at 516.5 nanometers, that green glow comets are famous for, and oxygen at 630 nanometers from water photodissociation. Organic molecules like methanol could hint at life's building blocks. And then there's the spin. Early data suggests a rotation period around 7.2 hours, like a cosmic top. If jets are asymmetric, they'll torque it, changing the period. Astronomers track this drift through perihelion. If it shifts smoothly by 2 to 3%, it's natural outgassing. Sudden jumps, that's when the plot thickens. But hold on, let's build the emotional stakes. Imagine the generations of stargazers who've pondered if we're alone, if the galaxy teems with worlds like ours. 3I/ATLAS isn't just a rock, it's a time capsule from another star, potentially billions of years old, carrying clues about how planets form, how chemistry varies across the cosmos. If its deuterium to hydrogen, D/H ratio in water strays far from our solar system's median, say wildly higher or lower, it confirms a birthplace in a distant stellar nursery. That could mean exoplanets receive volatiles differently, leading to Venus-like hellscapes or Earth-like oases. The dust's polarization, how light scatters off grains, tells if it's fluffy, weathered by eons in interstellar space, or compact and fresh. High polarization rising with phase angle, million-year-old space fluff. Low, something anomalous. Now for the heartbeat of this narrative, 5 falsifiable predictions that anyone can track as data rolls in. These aren't guesses, they're testable claims grounded in physics, turning speculation into science. First, CO2 dominance holds steady. JWST's high ratio shouldn't flip post-perihelion. If it does, extraordinary chemistry is at play. Second, dust polarization matches ancient fluff, rising beyond Oort cloud norms as the object shifts position. Third, spin drifts predictably. 2 to 3% change from asymmetric jets, calculable from outgassing rates. Fourth, isotopes scream foreign. D/H outside our bands, a cosmic passport from afar. Fifth, radio silence. SETI scans worldwide from Green Bank to FAST listen for coherent signals. Natural comets buzz with noise. Anything structured, game changer. As October looms, the drama peaks with the Mars flyby on October 3rd, 2025. 3I/ATLAS will skim just 30 million kilometers from the red planet, closer than any Earth view, allowing ESA's orbiters to capture high-res spectra and images. Their UV and IR instruments might even spot meteors, interstellar dust shedding into Mars' atmosphere, burning as alien shooting stars. Imagine that, material from another sun streaking across an alien sky captured by our robots. The spectral streaks would differ, unique compositions, isotopes. It's a long shot, but if it happens, it's poetry in data form, proof of interstellar origins via simple, breathtaking light. Yet, science thrives on forks in the road. Path A, natural wonder. The high CO2 fits a CO2-rich parent system. Early activity from low sublimation temps. Dust fluffy from cosmic ray bombardment. Spin and motion match jet models. No residuals after accounting for radiation pressure and thermal lag. We learn comet formation varies wildly, advancing astrobiology. Path B, the what if. If 3 red flags persist, linear features in denoised images, stubborn anomalies in motion, though current data shows none. Isotopes inexplicable. Then we hypothesize engineered origins. Not claim, but test. Harvard's Avi Loeb has floated this, linking it even to the 1977 WOW signal, suggesting 3I/ATLAS's position then aligns. But NASA debunks alien claims, emphasizing classical cometary signs. Extraordinary evidence required. Pacing quickens as we address probabilities. Its retrograde orbit aligns near Earth's plane, a 2% chance for random visitors. Threading past Venus, Earth, Mars, Jupiter, stacked odds seem suspicious. But in a galaxy of 400 billion stars, trillions of ejections, Monte Carlo sims show such alignments naturally. Improbable, not impossible. Nature's weird. Black holes, quantum weirdness proved real. We test, not intuit. Transparency reigns. Verify via JPL horizons for positions, mast for raw Hubble/JWST data, ESO archives for spectra, minor planet center for amateur inputs. Challenge: fit gravity only model, add pressure, jets, see residuals. Pipelines open, dark frame subtraction, sigma clipping, reproduce, audit. 3 verdicts seal it. Isotopes match or mismatch solar norms. Polarimetry, fluffy or compact. Motion, residuals vanish with jets. By November, post-perihelion data clarifies. Why care? Implications ripple. If CO2 heavy, exoplanet models shift. Different habitability? Climates. Planetary defense validated. ATLAS spotted early, networks coordinated. Vera Rubin Observatory online soon, may find dozens more. Need faster protocols. Fundamentals: hyperbolic path equals interstellar. CO2 early activity. Green glow from C2. Size flux from coma. Jets accelerate. Polarimetry reveals texture. Isotopes birthplace. As of September 29th, 2025, the interstellar comet 3I/ATLAS continues to captivate the global scientific community with a flurry of new observations and analyses that deepen its mysteries while grounding them in rigorous data. Fresh images from ground-based observatories, including the University of Nariño Observatory in Colombia, captured on September 20th, reveal a developing small tail alongside the persistent coma, but eagle-eyed astronomers have noted faint moving specks nearby. Could these be fragments breaking off due to increasing solar heat, companion objects ejected from the same distant stellar system, or mere imaging artifacts from cosmic rays or atmospheric interference? Peer-reviewed studies remain cautious, emphasizing that no confirmed fragmentation has been documented yet, only enhanced gas and dust emissions as the comet brightens to around magnitude 10, making it accessible to amateur telescopes under dark skies. Meanwhile, Harvard astronomer Avi Loeb's latest blog post on September 25th highlights the object's anomalous mass, estimated at over 33 billion tons based on the surprising lack of non-gravitational acceleration. In typical comets, outgassing should propel it noticeably, but here, the massive nucleus, potentially spanning 5 to 20 kilometers, resists such perturbations, prompting comparisons to denser, perhaps rocky cores rather than the fluffy ice balls we're accustomed to. This mass anomaly, Loeb argues, could imply an origin in a high-density stellar nursery or even exotic physics at play, though mainstream NASA reports counter that it's simply a scaled-up version of Borisov with classical cometary behavior amplified by size. Adding to the intrigue, predictions from solar physicists suggest 3I/ATLAS is on a collision course with a coronal mass ejection CME from the Sun around late September or early October, a plasma burst that could superheat its surface, triggering explosive outgassing or even structural changes. Imagine the comet's icy veneer cracking under the assault, releasing plumes of volatiles that might alter its spin or trajectory in ways our models haven't fully anticipated. ESA's Mars orbiters are gearing up for the October 3rd flyby at just 30 million kilometers, promising high-resolution spectra that could detect any CME-induced alterations in real time, while SETI protocols persist, with radio scans yielding only cosmic static so far, quelling wild speculations of artificial signals. Public discourse on platforms like X buzzes with unverified claims. Some users report regular 17-minute energy pulses, debunked as sensor noise. Others link it to UAP sightings near airports, weaving narratives of alien probes slingshotting via Mars toward Earth, but orbital simulations from JPL Horizons confirm no such maneuver. with the comet's path safely arcing past Earth at 1.8 astronomical units on December 19th. Yet, as pre-discovery images from June 2025 surface, showing marginal coma even then, questions arise about its dynamically old nature. Has this wanderer been sandblasted by interstellar radiation for billions of years, preserving ancient chemistry from a star long gone? The Vera Rubin Observatory, now operational, hints at detecting more such visitors soon, potentially dozens in the coming decade, urging upgrades to rapid response protocols across NASA, ESA, and amateur networks. This evolving story isn't just about one comet, it's a window into galactic diversity, challenging our assumptions about comet formation, volatile delivery to exoplanets, and the frequency of interstellar exchanges. Each new data point a thread in the tapestry of cosmic history, reminding us that the universe's secrets unfold not in grand revelations, but in the patient accumulation of photons and spectra from distant specks of light. Diving deeper into the whirlwind of debate surrounding 3I/ATLAS, as of this very day, September 29th, 2025, the scientific community finds itself at a crossroads where empirical evidence clashes with tantalizing what-ifs, fueling everything from peer-reviewed papers to viral X threads that blend astrophysics with speculative fiction. Harvard's Avi Loeb, never one to shy from controversy, doubled down in his September 25th Medium article on the comet's lack of non-gravitational thrust, implying an anomalously massive body, suggesting that if natural jets can't explain the stability, perhaps we're dealing with something engineered, maybe a relic probe from an ancient civilization, its trajectory eerily aligned with the galactic rest frame, and even retroactively positioning it near the 1977 WOW signal's origin, though he stresses this as a hypothesis demanding extraordinary evidence like unusual radio emissions or geometric anomalies in denoised images. NASA, in contrast, issued a firm debunk on September 11th via The Guardian, dismissing alien theories by pointing to Hubble's July 21st teardrop-shaped dust cocoon and JWST's August 6th infrared data showing classic photodissociation of water and CO2 with no signs of artificial structure. Instead, they frame it as a major anomaly in mass alone, potentially a fragment from a disrupted exoplanet or a dense aggregate from a carbon-rich disk, with size estimates refined to no more than 3.5 miles across based on Astrophysical Journal letters. Social media amplifies the divide. X-users like @PatrickQ Jackson speculate on Mars slingshots for Earth approaches, refuted by orbital math showing a 28 million kilometers miss, while at For Whatever Time shares September 20th footage hinting at faint companions. Debated as possible fragmentation from pre-discovery activity noted in a September 12th astrobiology paper, or just optical illusions amid the comet's unusual polarization, which scatters light in ways suggesting weathered, fluffy grains from eons adrift. The impending CME interaction, forecasted by IFL Science on September 25th, adds urgency. If the solar eruption strips away outer layers, revealing a metallic core or triggering green glows from diatomic carbon, as seen in BBC Sky at Night's compiled images from VLT, Hubble, JWST, SPHEREX, and Gemini, it could confirm natural origins or escalate mysteries if unexpected spectra emerge, like unexplained nickel vapors or cyanide spikes. Broader implications ripple outward. ESA's FAQ on September 24th underscores naming conventions. 3I for Third Interstellar, ATLAS for Discoverer, while the debrief's September 25th piece posits 3I/ATLAS isn't alone, with models predicting more frequent visitors as surveys like Vera Rubin ramp up, potentially reshaping planetary defense strategies and astrobiology models if CO2 dominance proves common, altering habitability zones around other stars. Amateur contributions via the Minor Planet Center database grow daily, with users challenging official fits, recreate residuals plots adding radiation pressure and thermal lag, and if stubborn deviations persist, the engineered hypothesis gains traction, though chi-squared stats favor natural jets. Amid this, ethical questions arise. Should we broadcast signals toward it, as some SETI advocates urge, or maintain silence per protocols? The Mars flyby looms as a pivotal moment, with ExoMars potentially capturing UV flashes from interstellar meteors, a poetic end for alien dust, while global collaborations exemplify science's collaborative spirit transcending borders in pursuit of truth. Whether 3I/ATLAS unveils galactic secrets or reinforces known physics, it unites us in awe, prompting reflections on our place in a vast, wandering cosmos where every visitor carries echoes of distant suns. Turning our focus to the intricate chemical makeup of 3I/ATLAS, as revealed by the latest spectral analyses on September 29, 2025. This interstellar comet presents a treasure trove of molecular signatures that challenge our preconceived notions of cometary evolution across the galaxy, with telescopes like JWST and Hubble unveiling a composition rich in carbon dioxide, carbon monoxide, water vapor, cyanide, and even atomic nickel vapor, a combination that hints at formation in a stellar environment markedly different from our own solar system's Oort cloud or Kuiper belt origins. The James Webb Space Telescope's mid-infrared observations from August 6, 2025 pinpointed an unprecedented 8:1 ratio of CO2 to H2O, far surpassing the typical 1:10 seen in local comets, suggesting that 3I/ATLAS hail from a colder carbon-rich protoplanetary disk where volatile ices like dry ice sublimated preferentially under minimal stellar heat, potentially from a red dwarf star or a distant galactic region where heavy elements were scarce, yet carbon compounds abundant, as detailed in a Smithsonian Magazine article highlighting the surprising abundance of nickel, which could indicate exposure to intense cosmic radiation or internal heating mechanisms not yet fully understood. Ground-based facilities such as the Very Large Telescope in Chile have detected cyanogen bands at 388 nanometers and the iconic C2 Swan bands at 516.5 nanometers, responsible for the potential green hue as solar ultraviolet light dissociates carbon molecules, while oxygen lines at 630 nanometers confirm ongoing water photodissociation, painting a picture of a dynamic coma where solar wind strips away layers, releasing these building blocks that might mirror the primordial soup seeding life on exoplanets billions of light years away. Organic molecules, including tentative detections of methanol and other hydrocarbons via high-resolution spectroscopy, raise astrobiological eyebrows. Could this visitor carry the same prebiotic chemistry that jump-started life on Earth, or does its foreign isotope ratios, still under analysis for deuterium-hydrogen deviations, point to radically different nucleosynthetic processes in its birth star? As the comet brightens, reaching magnitude 10 by mid-September per EarthSky reports, with Gemini South's September 4th image showing streaked background stars due to fixed tracking on the comet's motion, these spectral fingerprints evolve, with predictions of intensified outgassing near perihelion potentially unveiling rarer species like formaldehyde or ammonia, testable through upcoming observations that could either align with natural interstellar comet models or flag anomalies demanding new theoretical frameworks. The absence of strong non-gravitational forces, despite this volatile activity, underscores the object's massive scale, implying a nucleus resilient to jet propulsion, perhaps layered with a protective regolith forged over eons of interstellar travel, bombarded by cosmic rays that altered its surface chemistry in ways our models are scrambling to simulate. This chemical narrative not only enriches our understanding of galactic diversity, but also fuels interdisciplinary collaborations, from chemists modeling sublimation rates to biologists pondering panspermia implications, all while the public watches, inspired by vivid images from NOIR Lab and NSF that transform abstract data into tangible wonders of the cosmos, reminding us that each spectral line is a story of stellar birth, ejection, and eternal wanderlust. Delving into the orbital intricacies and mass estimations of 3I/ATLAS as of September 29, 2025, this cosmic nomad's hyperbolic path through our solar system offers a masterclass in celestial mechanics, with its velocity of 61 kilometers per second at discovery confirming an unbound trajectory originating from the direction of Sagittarius, potentially the galactic center's influence, as archived pre-discovery observations from Atlas telescopes worldwide and the Zwicky Transient Facility refine its ephemeris to show a perihelion around late October at approximately 1.4 astronomical units, safely distant yet close enough for detailed scrutiny. The lack of detectable non-gravitational acceleration, with orbital residuals under 0.028 arc seconds across 4,022 observations, as noted in Avi Loeb's September 25th Medium post, implies a staggering minimum mass of 33 billion tons, necessitating a nucleus diameter exceeding 5 kilometers assuming solid density. density, a figure that dwarfs predecessors like Oumuamua and Borisov by 3 to 5 orders of magnitude and prompts questions about its formation, perhaps as a planetary fragment ejected during a stellar close encounter or a rogue world stripped of its atmosphere, now masquerading as a comet with its icy veneer. Monte Carlo simulations of interstellar object populations, updated with Vera Rubin observatory projections, suggest such massive interlopers are rare but statistically plausible in a galaxy teeming with trillions of ejected bodies. Yet the alignment of its retrograde orbit within degrees of the ecliptic plane, a mere 2% probability for random visitors, fuels probabilistic debates. With stacked odds of planetary flybys, Venus, Earth at 1.8 astronomical units on December 19th, Mars at 30 million kilometers on October 3rd, Jupiter, appearing suspiciously fortuitous, though computer models affirm natural occurrences over cosmic timescales. Radiation pressure from sunlight, thermal lag and outgassing jets, and potential interactions with solar wind or CMEs forecasted for early October add layers to dynamical models, where chi-squared fits incorporating these forces eliminate most residuals, supporting a natural explanation while leaving room for anomalies if post-perihelion data reveals unexpected drifts. Amateur and professional astrometrists contribute via the Minor Planet Center, tracking positional data that refines predictions, with JPL Horizons providing public ephemerides accounting for relativistic effects and light time delays, enabling anyone to simulate its path and audit claims of engineered maneuvers, which current data refutes despite speculative links to the 1977 WOW signal. This dynamical profile not only tests gravitational theories, but also enhances planetary defense systems, as ATLAS's early detection demonstrates seamless coordination among global networks, preparing us for the influx of dozens more interstellar objects expected in the next decade, each a probe into the mechanics of stellar ejections and galactic migrations that shape the universe's grand architecture. Recap predictions. CO2 persists, dust fluffy, spin predictable, isotopes foreign, radio noise. Mars delivers imaging, ground scopes, isotopes/spin. Track with us. What would you test first on Mars orbiters? Share in comments. Your ideas could spark discussions. This narrative isn't over. As 3i/ATLAS hurtles on, it reminds us of our cosmic humility. Whether natural marvel or deeper mystery, it unites us in wonder. Like, comment your theories. Does it change how you see the stars? The universe awaits.